This is example 14.3 from Discovering Design with Chemistry. And it says, in the previous example, we learned that the change in H for the following reaction is negative 189.2 kilojoules. And then they give the decomposition of hydrogen peroxide. Did I say the right name? Yeah. And then it asks us, if 500 grams of hydrogen peroxide decomposes, how much energy is released? So now we're combining stoichiometry with the enthalpy that we've been working with. So let's go ahead and look at it. This number is negative, so we know that this is an exothermic reaction. And we had already determined that also in the last problem. So because of that, we know that energy is being made. It's coming out of this reaction. And so if we wanted to put that energy somewhere, we could add it as a positive number on this side at the end. We can think about energy as if it's a product and just stick it over there with the other products. The negative sign on that change in H just tells us where to put the energy. We know that negative means exothermic, therefore it's a product, or it's released, like sort of like a product would be. If it had been positive, that would have been an endothermic reaction, which means it like kind of consumes or takes in energy. And so we need to put that on the reactant side, but that's not the case for this problem. So what do we do from here? We've been given a mass of one of our only reactant, and they want to know how much energy is released. Well, this reaction right here tells us that for every 2 moles of H2O2 that we put through the reaction, we're going to have 189.2 kilojoules of energy released. So we need to start by kind of converting some things from what they are given to what we need. So we're given that this is, let's put it up here, 500.0 grams. So let's figure out how many moles that relates to so that we can see how it compares to the problem. All right, so we've been doing this for a while. H is 1.01 AMU, O is 16 AMU, and we have 2 of each of those. And so you know how to do the conversion, but the molar mass of H2O2 is just going to be 2 times 1.01 plus 2 times 16. And so that's going to be 34.02 AMU, or in other words, 34.02 grams per mole. So if we were given 500 grams of H2O2, we can take what we just found, just like we did in previous chapters. We want to get rid of grams. We want to change it to moles, and then we can use this conversion relationship. So there's 34.02 grams for every 1 mole. And then we can work through that. The grams is going to cancel. Let me add in my extra little things. There we go. And what we're going to find out is that 500 grams is the same as 14.70 moles of H2O2. Sorry I didn't pull out the calculator for that, but I wanted to not spend forever doing this one. All right, so let's fill that in over here. So we have 14.70 moles of this that we're working for. All right, well, let's make another. What we need to figure out is, we know that 2 moles, let's pick a different color. 2 moles of H2O2 is going to produce 189.2 kilojoules of energy. And so how much would 14.70 moles of the same thing, H2O2, how much energy would that produce? You can probably see that you can line it up like a ratio, but what we're going to do is we're going to use a conversion relationship. We're going to kind of say, instead of saying that it produces, oh, that was not, yes, that's what I want. We're going to change that and say this equals, that these two we can convert using this. So let's go back to our 14.70 moles is how many we have. And we know that for every 2 moles of this is how much energy we have. So let's kind of work it as if we have as if we're just converting from moles of something to kilojoules of the same something. It's not exactly what we're doing, but the idea still works. You know what? I don't know if I can move this. Can I select this? Let's move all this mess down, because that's a little bit too close to our previous stuff. All right. All right, so we want to get rid of moles of H2O2, and we want to swap it out for kilojoules of our energy. For every 2 moles of H2O2, we have 189.2 kilojoules of energy produced. Our moles are going to go away, and then we can just do the math. So, oh, I pulled out my phone calculator. I realized you can't see my phone calculator. That's not going to be very useful. All right, so 14.70 times 189.2 divided by 2. All right, so in this case, it's all multiplication and division. The 2 moles is an exact number. We can't have a piece of a mole, so we just need to worry about the other ones, which each have 4 significant figures. So our answer, we're going to keep 4 significant figures, which are these first 4 right here. So let's let the 6 tell us that we're going to round up the 0 to 1. We have 1391. So 1391, and that is kilojoules. So when we have 500 grams of H2O2, we have 13.91 kilojoules of energy that's released. So when you know the change in enthalpy of a reaction, like we knew here, we knew what that was, you can just put it in the equation on the correct side. If it's exothermic, if it's producing energy, let's put it with the products. If it's endothermic, you need to put it with the reactants, and then you can use it as if it's just another piece of your stoichiometry like we did in previous chapters.